In Chapter 6, we will discuss how to draw Lewis dot structures, how to figure out the molecular shape from those Lewis structures, and then discuss electronegativity, bond polarity, molecule polarity, and how those two things can influence intermolecular forces. We will skip section 3 of chapter 6, which is resonance structures. We will start by discussing how to draw Lewis dot structures, and we will be doing a lot of examples of these in class. We have mentioned this before, that main group elements try to achieve stability by becoming isoelectronic with noble gas elements, meaning they try to lose or gain electrons or share electrons to achieve the same noble gas configuration as the gas that's either the noble gas that's closest to them. When they reach the noble gas configuration, they typically have a full electronic shell. And for all intents and purposes for this class, we will assume that they try to get 8 electrons around them, which is also known as the octet rule. Octa meaning 8. The octet rule then states that the atoms, most atoms in the periodic table, at least the ones that we're going to deal with, will lose, gain, or share electrons so that they will have 8 electrons around them. Now they can form covalent bonds by sharing those electrons. Then we can count the shared electrons for either atom, because technically, since they're sharing them, they belong to both, and allows both atoms, or all the atoms that participate in the bonds, to obey the octet rule, except for hydrogen, because hydrogen can only accommodate 2 electrons and no more. So hydrogen is an exception. We will talk about other exceptions to the octet rule when we get there, but for right now, we'll focus on the octet rule. Here's kind of a simple example of the chlorine molecule, Cl2 molecule. Remember that chlorine is group 7, which means it has 7 valence electrons, and it's only 1 electron away from having a full a noble gas configuration of argon. And to do that, it only needs 1 electron. Well, this chlorine only needs 1 electron. This chlorine only needs 1 electron. Each of them have 1 unpaired electron, but when they come together to form a bond, they can share each other's electrons, and they form this bond right in the middle here. This electron, if you will, coming from this chlorine, and the bottom electron coming from this chlorine. So the left chlorine counts all the dots in the blue circle as its own, including the one that is shared by the right-hand side chlorine. The right chlorine atom counts all the dots in the pink circle as its own, including the one that is coming from the chlorine on the left. So those middle ones are shared equally by both, but they both count them as their own, and therefore they fulfill the octet rule. So 2, 4, 6, 8, 2, 4, 6, 8. They have 8 electrons around them. They're following the octet rule, and they're happy. Let's talk a little bit about terminology when it comes to Lewis dot structures. Here's the molecule carbon tetrachloride. It's a carbon with 4 chlorine atoms surrounded by it. The element that is the atom that is in the middle here is called the central atom. Now, a molecule may have multiple central atoms, but in this molecule, we only have one. It has the element carbon. So this is my central atom. And it makes sense because it's located centrally. Other atoms are bonded to it. That's why it's called the central atom. On the other hand, the other atoms that are bonded to the central atom are called terminal atoms. Terminal meaning at the end. Typically halogens, now this is typically, but halogens, so group 7 atoms, and hydrogens are going to be terminal atoms. They like to be on the ends because they have lone pairs for the halogens, and hydrogen can only accommodate 2 electrons, so it can only fit one bond at a time. This molecule then has 4 terminal atoms, and they are all chlorines. Now, they can be a hydrogen or 2 hydrogens, they can be other ones, but in this molecule, they're all the same, and they're chlorines. Now, you will see these dashes here around the central atom, and these are called bond pairs. These bond pairs, so these dashes, represent 2 electrons, and those are electrons that are being shared equally between, well, in certain cases equally, in others not equally, but they are being shared between the central atom and the terminal atom. These two are those shared electrons. Now you can see that my central atom, having 4 dashes around itself, it has 8 electrons. 2, 4, 6, 8. Remember that a dash represents 2 electrons. Out of those 2 electrons, one comes from the central atom and the other comes from the terminal atoms. But remember that those shared electrons are counted both for the central atom and for the terminal atom, just like we talked about in the Cl2 molecule. And finally, you will see these dots around some of the atoms in the Lewis dot structures. Those dots represent lone pairs of electrons. Those are electrons that are not being shared, and they have to be paired. The electrons have to be paired. Otherwise, we have a very reactive molecule called free radical. Those electrons that are being shared are not lone pairs, but lone pairs belong solely to the atoms that they are surrounding. In this case, the chlorines, each of the chlorines, has 3 lone pairs, 2, 4, 6. Those 6 electrons belong only to this chlorine. Now this molecule, carbon tetrachloride, has 12 lone pairs, 3 for each of the chlorines, and these make a total of 24 non-bonding electrons. These electrons are not participating in any bonds, only the ones that are in the dashes. These are some of the words, the terminology that we're going to use when we talk about Lewis dot structures. Make sure that you understand what each of them means. Okay, let's talk a little bit about the steps that we're going to use to draw Lewis dot structures. First, we start with the molecular formula and we write the symbol for each of the atoms in order how we expect them to be arranged in the molecule. Okay, this is the drawing a skeletal structure, right? Then we use dashes to draw bonds between atoms in the skeletal structure. And those dashes, remember, represent 2 electrons. Now we count the total number of valence electrons that are being donated by all the atoms in the molecule, just the valence electrons. Remember, we determined the valence electrons by looking at the group number. If it's group 1, it will have 1 valence electron. If it's group 2, it will have 2. Group 5, it will have 5, etc., etc. For each of the bonds that or the dashes that we arrange, we draw in the skeletal structure, remember that those represent 2 electrons. So then we take all of the total from the dashes that we've drawn, we add all of those bonds together, multiplied by 2, those are the total bonding electrons, and then we subtract them from the total number of valence electrons that we determined in step 2. The result then, what's left over, is the number of electrons that we must distribute as lone pairs. We distribute those as pairs of dots to complete the octet in the atoms in the structure. But remember, hydrogen only gets 2 electrons. It does not get 8, so it doesn't have lone pairs. Only 1 dash. Typically, the halogens will have 3 lone pairs. Group 6 will have 2 lone pairs, etc., etc. We will also talk about those elements that are exceptions to the octet rule, but not quite yet. Then we might have leftover electrons, or we might not have enough. Once we distribute lone pairs, we may not have enough to satisfy the octet rule for all, the central atom and some of the terminal atoms. To fix that, we can share more than one bond between atoms. We can have single bonds, which is represented by 2 electrons. We can have double bonds, which is represented by 4 electrons, or 2 dashes between the central atom and another atom. Or we can even have triple bonds, which are 6 electrons that are being shared. We will get to that in the examples that we're going to talk about. So let's take a look at some examples here. Here's my molecule, Cl2. Well, let's first arrange write the symbols. We have 2 chlorines, so we write 2 Cls side by side. Over here, we have HCl. We have a hydrogen, we have a chlorine, so we write them side by side. There's only one way to arrange these because these are diatomic molecules. Then we can put a dash in between here, between the chlorines and between the hydrogen and the chlorine here. Now, the next step is to sum the valence electrons for all the atoms. We know groups 7 electrons, group 7 atoms, which chlorine is a part of, have 7 electrons, 7 valence electrons. And since I have 2 chlorines, I have 7 from one and 7 from the other, a total of 14. For HCl, hydrogen is group 1, so it brings 1 electron. Chlorine is group 7, so it brings 7 valence electrons for a total of 8. And then for each of the bonds that we drew in the structure, we subtract 2 electrons. Here we would have a dash. That's the bond between the 2 chlorines. Well, since we only have 1 bond, we would subtract only 2 electrons from my total. 14 minus 2, I have 12 electrons left to distribute. Over here, I had 8 minus 2 from the bond here would give me 6 electrons to distribute. Now remember, the total valence electrons is the total number of electrons that I have to count around all my atoms. I cannot have more and I cannot have less. I have to use just the total amount of valence electrons that is contributed by all the atoms. Since I have 12 electrons left from the molecule Cl2 to distribute, then I start distributing lone pairs, and I put 2, 4, 6, so 3 lone pairs on this chlorine and 3 lone pairs on this other one. And now let's count the total number of electrons that I have around both chlorines. 2, 4, 6, 8, 10, 12, 14. which means I've used up all of my valence electrons. Exactly. I have not used less and I have not used more, so I'm good there. The next step that I have to make sure I've done correctly is to count the electrons around each atom and figure out if I'm following or satisfying the octet rule. 2, 4, 6, 8. So this chlorine is happy. Now let's move to this chlorine. 2, 4, 6, 8. So this chlorine is also happy because it has 8 electrons. Remember that those dashes or the electrons that are shared, they count for both atoms that are sharing them. Let's take a look at HCl. I have only 6 electrons to distribute, and I know that hydrogen cannot handle any lone pairs. Therefore, all those 6 electrons must go on the chlorine. So I distribute them as lone pairs, 1, 2, 3. And now let me count the total number of electrons. 2, 4, 6, 8. That is how many electrons I had to begin with that I needed to use. My hydrogen has 2 electrons around it, and hydrogen is happy with 2. Then my chlorine has 2, 4, 6, 8 electrons, which means it's satisfying the octet rule. And this molecule is done. Now, I can have structures or molecules that have more than a central atom, or I can have polyatomic molecules, right? In polyatomic molecules, there might be more than one possible way to arrange the atoms, and I have to find the best way to arrange them. The rule that I need to follow, at least most of the time, is to find that unique atom, the one I have the least of, and make them my central atom. Then I arrange the other atoms symmetrically around the central atom and draw a bond between the central atom and every other atom that is around it, every terminal atom. The atoms that surround a central atom, we mentioned that earlier, are terminal atoms. Let's take a look at some more molecules, CCl4 and H2O. Note that these are not diatomic molecules anymore. For CCl4, I have 5 atoms altogether. When I'm looking at this molecule, I have only 1 carbon, but I have 4 chlorines. That means that carbon is the least of, and hopefully this will be easy to remember, but since carbon is the one that I have the least of, that will be my main central atom. So I place that in the middle. And then I distribute the other molecules of chlorine just around my central atom as terminal atoms and draw dashes to tie the central atom to each terminal atom. I do the same for H2O. Note that I only have 1 oxygen, but I have 2 hydrogens. So I put the oxygen in the middle because I have less of the oxygen and more of the hydrogen. And then I distribute the hydrogens around the oxygen and draw dashes to tie the oxygen to the hydrogens. Let's figure out the total valence electrons that I have to work with for both of these molecules. Okay, now carbon is group 4. That means I get 4 electrons, 4 valence electrons that are contributed from the carbon. Then I look to chlorines. Chlorine is group 7, but I have 4 of them. So that means I have to multiply 7, which is the number of valence electrons that each chlorine brings in, by 4. So 4 times 7, that gives me the total number of valence electrons available or contributed from the chlorines. That's 28 plus the 4 from the carbon, giving me 32 total valence electrons that I have to distribute around the CCl4 molecule. Let's figure out how many I need for that water. Oxygen is group 6, so it brings 6 valence electrons. Hydrogen only brings one, is group 1, so only brings 1 electron, but I have 2 hydrogens, so I have to multiply that by 2. 6 from the oxygen plus 2 times 1 for each hydrogen, giving me a total of 8 electrons. Now, let us subtract the electrons that I've already used up to form bonds between the central atom and terminal atoms. I have 2, 4, 6, 8 electrons that I've used in bonding. These are bonding electrons. So I take my total, which is 32, minus 8. That gives me 24 electrons to distribute around the chlorines. Now, what about the water? 8 minus 2 plus 2, 4, minus 4 electrons. I have 4 electrons left to distribute. Now, remember, we'll do water first because it's easier. Remember that the hydrogens only take 2 electrons. Hydrogens do not take lone pairs. I do not want to see any Lewis-Dawes structures where the hydrogens have lone pairs. That is a big no-no. Hydrogen, this hydrogen has 2 electrons, this hydrogen has 2 electrons, so they're happy. Therefore, these 4 electrons must go on the central atom, which is oxygen. So I put them as lone pairs, 2 and 2, 4. And now I figure out if all of my atoms are happy. We said hydrogens have 2 and they're happy with 2. What about my central atom? Is it following the octet rule? Well, let's count. 2, 4, 6, 8. It has 8 electrons around it, so oxygen is happy. It's following the octet rule. I've used up all of my 8 electrons, 2, 4, 6, 8, and this molecule is done. Let's now distribute the 24 electrons that I have left over, the non-bonding electrons, in CCl4. Well, what if I distribute 3 lone pairs per each chlorine? 2, 4, 6 times 4, because I have 4 chlorines, 24 electrons. Now let's count to see if I have used up all 32 electrons. 2, 4, 6, 6 for each chlorine, multiplied by 4, that gives me 24, plus 2, 26, 28, 30, 32. So I've used up all of my valence electrons. Now, the last step that I need to do is to assure myself that all of my atoms have 8 electrons around. 2, 4, 6, 8 for each chlorine. The chlorines are happy. What about the carbon? 2, 4, 6, 8. So the carbon is also happy. I've used up all my valence electrons, and this molecule is done as well. In Lewis structures, then, we talked about this. A dash represents a pair of shared electrons, known as bond pair or bonding pair. The dots represent the non-bonding electrons. They belong to that particular atom only, not being shared with any others. These unshared pair of electrons are known as lone pair or non-bonding pair. Let's look to some examples of polyatomic ions. Remember, we have a table of polyatomic ions. When we have polyatomic ions, we might have a charge that we have to deal with. For example, NH4 has a charge of plus. So how do we deal with this plus? Or ClO has a charge of minus. How do I deal with that negative charge? Well, to deal with charges of polyatomic ions, when we calculate the total valence of electrons that I have to work with, I have to either subtract an electron for every positive charge or add an electron for every negative charge. Let's first kind of draw skeletal structures. I have nitrogen in the middle because that's the least atom, the least number of atoms that I have. I have 1 of these and 4 of these, so I put nitrogen in the middle. Plus, we know that hydrogen is always a terminal atom, so hydrogen goes on the outside. And then this is a diatomic molecule, pretty simple. I have the chlorine that is attached or bonded to the oxygen. Now let's count the total number of electrons. Nitrogen is group 5, so it's bringing 5 electrons. Each hydrogen brings 1, and I have 4 of them, so 4 times 1. That gives me 9 electrons. However, I have a plus charge, so I have to subtract 1 for every positive charge, which is plus 1, right? I have 1 positive charge, so I subtract only 1. So subtract 1 to account for the plus 1 charge on the ion. Gives me only 8 electrons to deal with. What about for the ClO? Chlorine is group 7, so it brings 7 electrons. Oxygen is group 6, so it brings 6 electrons. However, it has a -1 charge, which means that I have to add an electron for every negative charge, giving me a total of 14 electrons. Now, I can write or draw dashes for bonding all the hydrogens around the nitrogen or bonding the chlorine to the oxygen. Let us account for all of those bonding electrons. Remember, each dash counts for 2 electrons, so 2, 4, 6, and 8. I subtract 8 from my total valence electrons. I subtract the bonding electrons, which in this case for NH4 plus is 8, giving me 0. So I've used up all of my valence electrons and I have none to distribute around the terminal atoms, which in this case are hydrogens, which makes sense. Hydrogen, they do not have lone pairs. Okay? When we draw polyatomic ions, we draw the structure, we put square brackets around it, and then we add the charge on the outside. So for ammonium, I have NH4, so N in the middle, hydrogens on the outside, square brackets, and then a plus for the charge. Now, my hydrogens are happy because they have 2 electrons each. The nitrogen is also happy because it has 2, 4, 6, 8 electrons around it. Let's finish the ClO minus. We determined that I have 14 electrons to work with, minus 2 electrons that I'm bonding the chlorine to the oxygen. So I have 12 electrons to distribute around both the chlorine and the oxygen. Let's distribute them as lone pairs. 2, 4, 6 here, 2, 4, 6. So 3 around the chlorine and 3 around the oxygen. That makes 12 electrons. So 2, 4, 6, 2, 4, 6. That's 12 electrons. And I have used up all 14 valence electrons. The last thing that I need to do is make sure that my atoms have followed the octet rule. So let's count chlorine first. 2, 4, 6, 8 electrons. So chlorine is happy. 2, 4, 6, 8. My oxygen is happy. When I draw the Lewis-Dawes structure of this polyatomic ion, I will write, so I'll draw the structure, write square brackets around it, and then put the charge on the outside. So it has a minus charge outside of the square bracket. And this molecule is also done. Okay, here is a sample problem. I will try to make this so that you can actually pick from a drawing of the correct Lewis-Dawes structure. If I am not able to, I will just draw or rewrite the question to include lone pairs and how to write the brackets, maybe the square brackets, etc., etc. But hopefully I will be able to write the Lewis-Dawes structures, and you have to pick from the correct Lewis-Dawes structure.